As yeah, oh, perfect. Yeah, as I understand, some of you are. There is kind of always this explore phase where you kind of seek out many answers, and then at the end of the day, you exploit them to kind of bring to find the answer that you want. And I use this as a metaphor, or kind of a loose analogy, that Grover search also does a very similar thing, because the very first step of the Grover search is a Hadamard tensor n. So you just spread yourself all over the Hilbert space that's available, and then you search for the correct answer. And likewise, Shor also has a Hadamard tensor n, and so you could kind of interpret that there's something interesting happening here, where both classical and quantum machines seems to be doing this thing, where they first kind of scramble information all over the place, and then they try and or scramble states all over the place, and they try and find something that's interesting, and then focus. Once they find the correct answer or whatever, they then target through interferometry to find to increase the amplitude in a local place that they can measure. So maybe these kinds of techniques can be generalized to metrology. This is basically to sensing theory. This is the story that I want to say to you. And so the motivation is to design a robust quantum sensor. So by robust, I mean the following, which is that there is no fine tuning. So for those of you who are aware of what quantum sensors are, there are initial states which are prescribed. I'll walk you through them, which are very, very finely tuned. So they're very specific superpositions of Hilbert space that you have to arrange. And then it acts as a very good sensor, which beats classical resources in the job that it does. But they're very difficult to make, and they can kind of collapse all over the place all the time, and so on and so forth. So if, at least at the first step, we can design sensors, or at least identify spaces where any generic state that you pick up, so you throw a dart and then it hits the board, and then any state that you've hit is a good sensor. Then this would be a step towards building sensors that are really field deployable, and then make them practical, because then you don't have to worry about kind of fine-tuning things. That's the idea. And so with that, let me just introduce sensing theory. So even if the particular results of my talk aren't particularly interesting to you, I hope that I share a little bit of the general story with you. And then talk a little bit about what's quantum about them, and then other works that have motivated us. And then finally, I flash my specific results, again, which we're writing up just now. Okay, so what's the general definition of a quantum sensor, right? And in fact, this is the general definition of a sensor with both classical and quantum. So the idea is you want to measure something like this, a magnetic field, which is induced by placing a permanent magnet somewhere. And so what you do is you have a little chip, maybe it's a MEMS device or something like that you bring over here, and then it produces a current in some device, and you stare at the current, and now you have to decide how much the magnetic field was. So mathematically speaking, what you're doing is you're actually generating a probability distribution in the space of kind of clicks, detector clicks, if you want, if there are multiple detectors, and they can have a skewness in the number of clicks that they generate. Or if you want to take the photocurrent, then you normalize, you add something to the, photocurrents are positive semi-definite numbers, so you just normalize them, and they're like a probability distribution. So you have a probability distribution that is generated, P of x, but it is parametrized by whatever it is that you're measuring. So if you shift the sensor a little bit, so you move it a little bit from here to here, you generate a different curve. Typically, it's not this dramatic. I've drawn essentially a cartoon for illustrative purposes. But now, what the whole story, the whole game of sensors is looking at this probability distribution. You have to figure out what the magnetic field was. That's the thing that you know how to measure. Those are the detector clicks. That's the thing that you desire to know. And so this game of parameter estimation, what you can to do the maths of it, what you do is you write a parameterized probability distribution. So you say that this is a probability distribution that comes from some parameter p phi of x, and this is the red one in this case. And then when I shift it from phi to p phi plus delta phi, I've shifted my probability distribution in some way. And now I need to look at these probability distributions and infer the underlying parameter. This is the problem of local metrology, which means I'm sitting at a place phi, and I'm just trying to build a really good sensor that detects drifts. So if I change phi, if I move my entire sensor over there, then there is a completely different kind of probability distribution sets that are generated, and I might have to change what I do in terms of measurements when I do the quantum or the classical one. But onward we go. So the formal theory of this, basically, I present to you in the next 2 slides, but here is the intuition of it. You can see that there is this red region, the region that I've colored in red, which is actually pretty useless because both the probability distributions, both the detector click probabilities in this region, 0 to some x star, look pretty identical. So if I was to look, I wouldn't look here to know whether I was at phi or phi plus d phi, because this is not the kind of correct place to look. But suppose I was looking at this clicks, these number of clicks, then at a detector value which is like x17 or x25, then suddenly what I see is that x25 jumps from almost being 0 to almost being like, let's say, 0.7 or something. This has no axes because it's a cartoon. So this jump is actually quite easily detectable on a device. So what I would do essentially, as at least first order argument, is I would say, hey, look at the 17th detector, ignore the first 5 because they're not going to do much. Look at the 17th detector, and the 17th detector, if it goes click, it's actually giving you information about the shift in phases, right? So for those of you who are in optics, this is exactly the game we play. Total number is typically conserved in linear interferometers. So if you measure total number, you'd get no information. But if you measure difference in number, n1 minus n2, the difference between 2 ports, it often has quite an amount of information. So there are good measurements and bad measurements, and this is, and in fact, even in measurements, there are good parts and bad parts of the measurement, and this is all I'm trying to convey to you. And then what you can do is you can basically take this whole thing and make a statistical theory for it. And the statistical theory is basically that you have a space of parameterized probability distributions, and you can define distance measures between these states. So you can say this is p phi of x and this is p phi plus d phi of x. And on the space of probability distributions, these are 2 points. And the question that you're asking is, when my magnetic field went from, 1 Tesla to 1.0001 Tesla, how much did the probability distribution move as a whole? Because that's the total underlying statistical distinguishability between the two phases, phi and phi plus d phi. And so you can actually write down basically distance measures. You can pick any one. And you can basically discuss the distance between these two probability distributions measures the quickness of change to delta phi, right? So this is the exact same philosophy of criticality and so on and so forth. That just as you are at a position which has great change, you are very, very sensitive. That's the same argument here as well. But here it's just couched in the probability theory language, so it can be small or large or whatever this number wants to be, as disconnected from phase transition theory. And what you can then do is you can define actually a formal, you can actually take the Kullback-Leibler divergence, which is one of the many measures of how far two probability distributions are. And you can do basically a Taylor series expansion. In light, I have written, don't do this if you're trying to actually follow the quantum Fisher information derivation. There are singularities here. But as an argument, as a pedagogical argument to quickly introduce the topic, this is actually a very fine argument. And then what you see is that the Kullback-Leibler divergence is a measure of how close two probability distributions are. If I plug in the same probability distribution, the Kullback-Leibler divergence is 0 because they're not the same point. Because distances are positive semi-definite measures, this first derivative is 0 at the minima. So in fact, the leading order term is the second derivative term, and that's the curvature of the Kullback-Leibler divergence. In optimization theory, we do this all the time, right? At the optima, essentially, you have a second order variation and not a first order. The first order is 0. And so that object is the curvature of the Kullback-Leibler divergence, and this is actually called the Fisher information. And this Fisher information is the fundamental statistical quantity that actually tells you how sensitive a sensor is, given that you have told me how you're measuring the parameterized probability distribution, parameterized by a phase phi, which is a stand-in for an electric field, a magnetic field, an acceleration, so on and so forth, whatever physical quantity that you're interested in. And so this is the argument that I just presented. Because of this kind of minima property, then these two are 0, and the leading order term basically just ends up being this quantity that you can massage a little bit and write in this form. And this form is basically the famous form of the classical Fisher information. Okay, so Now, what makes it quantum, right? Everything I've just said is about probability theories. So what makes it quantum is the fact that we have to make contact with quantum. So this is the reason why now I have appended, I've written I as I classical, the exact same formula from the previous slide. And I classical is this guy right here. What makes it quantum is basically, first you just realize that the probability distribution here is simply the trace of some density matrix that is time evolving. So I have an input density matrix into an interferometer, and then it's picked up a phase, and that phase that's on the other side I'm measuring with some operator A, and A has detector outcomes X, and that's what I call the probability of getting X given that my parameter was phi. Right? Is this clear? And so the parameterized probability distribution, if I want to write a formal quantum equation for it, this is what I would write. And this is not quantum yet, because because all this does is maps what I did in quantum to the classical probability distribution. I haven't yet used quantum resources, right? An electron is quantum, but it's not considered a quantum resource unless you have coherence and other things in it. So now what you can do is you can take this classical Fisher information, which is the classical distinguishability of the probability distributions, and you can maximize overall measurements, right? And again, the intuition is exactly the one that I just presented before. If you have number conserving interactions, measuring the total number doesn't help you at all. So there are bad measurements you can really work out very easily, which means there are good measurements. And so you maximize over all possible theoretical measurements, which are all possible POVMs. And what you get is the maximum amount of statistical distinguishability that you can extract, given that your density matrix is parameterized this way, rho phi. Right? That's the whole game. So I'm fixed in the input state that I make, and I'm fixed in the Hamiltonian that generates the phase evolution. I fix these two just for this argument, for this slide. And then I say, given those two resources, what I have to basically even ask questions about good sensors versus bad sensors is actually to look at this parameterized probability distribution, compute something like the Kullback-Leibler divergence, actually the quantum Fisher information, and then which is the maximization over all possible classical Fisher informations, maximized over all possible measurements, right? So it just says I have an embedded state, a phase embedded state. What's the best you can do to extract all of the information? That's it. That's the entire argument. So this quantity, the quantum Fisher information, is essentially the workhorse of most of quantum metrology, because this is kind of the need of the hour. And this is not even yet the best quantum mechanics can do. This is just the best that, given an input state and given a Hamiltonian, that you can achieve. And now you can also go ahead and optimize the input state. Typically, you don't optimize the Hamiltonian. People have played around with this as well, but it's not practical to optimize the Hamiltonian, because what you're interested in is sensing, let's say, a physical quantity where you don't have too much control over what is happening, right? So if you have a biological sample and you want to send light in and measure basically some property of the biological, you don't have how the light interacts with the matter is just some fixed Hamiltonian that you can't touch. Now you can engineer the light to go in, and you can build very good detectors on the back end or the front on the reflection plane, but you can't touch the Hamiltonian that is basically just the water in the biological sample interacting with the quantum light that you've given it. So typically the Hamiltonians one doesn't touch, but the others you can optimize, and if you optimize, you get essentially the best sensors that quantum mechanics can produce, and that's basically the way the theory goes. Now you can write this in another way, which is you can basically just do an error propagation formula for it, which is you can say the variance of the error times the derivative of the measured quantity with respect to the phase that I want to measure squared is the variance of the measured quantity. And if you just rearrange it, you get a formula. And this is what experimentalists like, because experimentalists know how to measure this. And so what you can do is you can formally kind of connect these two by saying that what this variance of phi, if you make some choices, it's called an unbiased estimator choice. So if you make an unbiased estimator, what this variance of phi is it goes as two things. One of them is lower bounded by two things. One is the number of measurements you take. This is understandable. If you just repeatedly measure something 5 million times, you just get better and better accuracy. But you can't go all the way to 0 because there's always something that dominates the noise. And the thing that dominates the noise is basically this classical Fisher information. It's the fact that the statistical distribution, you have to infer from the statistical distribution the unknown parameter. And unless the unknown parameter phi and phi plus d phi produce orthogonal probability distributions, you will never have perfect distinguishability. They're always overlapping somewhere, and so you're a little confused whether this data was produced from this guy or this guy. And so there's always a little bit of unknowability there. And that uncertainty is captured by the Fisher information here. And all that this formula says is if you now optimize over quantum resources, then you get the lower bounds on basically how well you can do. So now whether this bound is achievable or not is a completely different story, right? Which I just want to also mention. Yeah, M is the measurement operator that I'm actually measuring.
So Risa, it's possible that these two are reversed? Sorry, I have fever, maybe I'm wrong. 1 over n is the lower and one of...
Sorry, Robert, I didn't catch the... Could you repeat?
In the quantum sensor, it's possible that the two bound you have written are actually reversed, or the signs are reversed?
Oh, it might be. Yes. Sorry, just give me 1 second. Yeah, they're reversed. Sorry. So no. So all I'm saying here is that in the quantum sensor regime, I'll come to this. Maybe I tend to confuse my inequalities, Roberta, but maybe I think I'm right, but let me just give me 1 more minute and I argue this and then I can tell you whether I'm correct or not. So I think this is correct. Let me just argue this. Yeah. N equals 100. Yeah.
You have the left 1 time and the right 100.
Okay. Yeah. So it has to be the other way around. Yeah. So this is the reason for this confusion is basically because there's a log involved in my head. But yes, you're right. This is the way to check. I draw the picture that's in my head so that I clarify this. So essentially what you're trying to do is you can plot minus log of the variance of phi versus the number of qubits. And this is the Heisenberg limit whose slope is basically 1. This is variance, so this is 2. And this is the short noise limit, standard quantum limit. And this is the Heisenberg limit. And essentially all I'm trying to argue with this, I think I got the inequalities wrong, I'm sorry, is basically anywhere here is a quantum sensor. So this is a bad sensor because this is doing worse than the best possible classical. And in fact, if you remember the LIGO floors, so the LIGOs has a kind of frequency versus error, and there is basically this kind of a thing there, a diagram there, which is basically as best LIGO can do. And for many, many years, they were hanging out over there. So if you translate that point into this diagram, it will be somewhere here. And then what I'm saying is that a sensor should be considered quantum if and only if, thanks Roberta for pointing this out, if and only if you are between basically the standard quantum limit and the Heisenberg limit. You cannot cross the Heisenberg limit because you'd violate the uncertainty principle. You'd actually be getting too close to, you'd be getting lower than how much information you're allowed to know from a quantum state. Okay, and just kind of to give respect where it's due, that's actually what an actual sensor looks like. And they're not even in the same units, and you'd have to actually convert all of this over. Because what they do is they sweep frequency. So this is a magnetometer, classical magnetometer. They sweep frequency, and then they're looking at basically some sort of noise spectrum that is coming out of it. And then suddenly you see peaks there. And those peaks are what they use to measure basically things like magnetic field. So this entire theory, if you wanted to kind of now take it to experiments, you'd have to do a little bit more work converting all of this to frequency space and stuff, which is irrelevant to our discussion. So anyway, the repetitions of the sensor are irrelevant. So essentially I just stick to this Q, which is the Fisher information. And then the only point I just wanted to make was, so magnetometers, accelerometers, sensors are not quantum because they're made of atoms, because that's not the logic of this argument. The logic of this argument is that you should have quantum resources actually working towards phase estimation, and that's this argument right here. and which I've presented here, but with the wrong signs. Yeah. Okay. So I can write this. I can actually write what this Fisher information is. For pure states, you can just calculate what the formula is, and it just turns out to be 4 times the variance of the Hamiltonian that is embedding the phase. So if I have a quantum state, can people who are on Zoom see the board?
No,
Okay, okay.
not clearly.
Okay, okay. I try to draw even cartoonishly big so that maybe I. So if I have a wave function psi naught, and then I have e to the minus I gt acting on psi naught, and that's a g theta g phi acting on psi naught, and that's my phase embedding. Then the variance of g in the pure state, 4 times the variance, is the Fisher information. It's just a formula you can derive with about 5 minutes of work. There seems to be a Zoom comment. Oh, is that board better? Okay, okay. I use that for the future. This one works well, yeah? Yeah. Okay. So what's the problem that we're trying to handle? If you now ask the community, how do you make how do you make these sensors, right? What they will tell you is make the following state, right? It's called a noon state. It's n photons or n particles entangled with each other. And if you were to make it using a quantum circuit, this is what you would do, right? Now, if you take this noon state and you try and perform basically the optimal measurements on this, so sorry, I forgot to mention this. So the Fisher information formula also comes built in with actually the measurement that you should perform to saturate that Fisher information. It's called the symmetric logarithmic derivative. The problem with this SLD, the symmetric logarithmic derivative, is that experimentalists don't know how to implement it. And essentially, this is one of the many problems of standard quantum sensing theory, which is that there are these mathematical theories that are derived, and then you go and talk to experimentalists, and they go, that's too crazy. You've just written something on a sheet of paper that I don't know what to do with. And so you need to tell me something a little bit better. Yeah. And so this is an example of something where you can actually do experiments with it. You can do metrology with it, but you can do metrology with it only because experimentalists essentially bypassed the mathematical theory and figured out measurements that still give you the Heisenberg scaling, so that produce quantum sensing scaling. So if you actually formally derive the symmetric logarithmic derivative, if you just follow the theory, it produces an operator that you don't know what to do with. And this is actually one of the huge problems with quantum sensing. So people have been trying to kind of bypass this. This is not the only problem. So the 2 problems that I've just mentioned are extreme sensitivity of like the initial state preparation, that you have to prepare yourself in some very careful way. And the other is basically that the final measurement is also tied to this extremely sensitive preparation. And so your the detector design on the measurement side is also very, very fine-tuned. And so these 2 fine-tunings is what I'm trying to get out of, basically. So with that, let me just proceed further. And actually what I want to show you is what other people have done in the field first. So what have experimentalists been doing, right? So theorists have all of this theory. What is the experimental procedure? So this is a spectacular paper. This was really just a groundbreaking paper in 2016 from Monica Schaller-Smith's group from Stanford. And her argument was the following, which is you take a spin coherent state on the generalized Bloch sphere, which is just cos theta ket 0 plus sin theta ket 1, but like for n of them, all of them together. And what you do is you squeeze along some direction. And so this she calls the twist untwist protocol. It's also called satin, which is what is signal amplification through time in reversal. So just has a funny name. So some other guys gave it a funny name, Saturn. So this twist untwist protocol is the following, which is you squeeze yourself along some direction, and when you squeeze yourself along this direction, what happens is that when you now have a phase embedding which is along the y direction, it essentially just rotates the state a little bit. And then what you do is you unsqueeze along the original direction. Now, because you're unsqueezing along a direction that the state no longer is in, you don't return back to the identity operator. So what ends up happening is you generate a lot of interferometric waves, which is this blue and red stuff on the Bloch sphere here. And what Monica Schulder-Smith, so this is inspired from bosonic sensing, which has the exact same trick as well, which is you squeeze along a quadrature, turn a little bit and unsqueeze, and it generates a lot of kind of wiggles on the Wigner function. So Monica Schulder-Smith's idea was then you measure the SY operator. And the cool thing about this paper is it proves that this method is essentially quite robust to having fluctuations in the number of measurements. So if you lose atoms in the measurement process, it doesn't care. And it goes beyond short noise. So in this diagram, it crosses this, but doesn't touch the Heisenberg line. But good enough for government work, right? So in terms of making progress towards very good quantum sensors, right? And this actually produced quite a tiny revolution in kind of all the atomic vapor cell community, anyone who could implement permutation invariant quantum states. So you'll notice that I just want you to notice that this Ry of phi actually, these are all collective spin operators. The whole argument is in the collective spin space. So this is just, I want you to notice this because it's going to become a story in like another 5 minutes. So now following this, what people did was basically they said, okay, we can do all kinds of things that are related to this. So this is basically some theory that has come out from here. So from Rothschild's group, where basically what they talk about is projecting over symmetric spaces to basically get the exact same answer. So it's a very quantum computing approach to the problem. And then there were many experiments that followed as well. So this is an experiment in ytterbium where basically they just try to just directly implement the twist untwist protocol. So Vladan Vuletech and several other people have experiments on this. Okay, so and then this also caused other protocols that have come up in response to this. So this is basically a double twist untwist protocol. So there are many things that you can do, and then you can ask questions about what if I twist untwist, twist untwist. You can now play games with this idea, basically. Okay, so the representations and so again, this is a thing that I just want to mention, which is once you have one of these techniques, which is this twist untwist or Noon state preparation or cat state preparation, whatever you want it, you have some crazy state that you have in your hand, which is then phase embedded. Now you have another crazy state. Now you need to measure it in kind of the optimal direction, right? This is essentially saying that I move a stick a little bit, and I need you to find the optimal direction to measure it so that you actually see the shift as much as possible and not kind of, let's say, from the top where, this shift doesn't look like much to you. And so that optimal direction is basically in the quantum, is basically the sensor design. And people have been trying to kind of also talk about sensor design. So this is, there are essentially 3 papers here. 2 of these I've represented, and the third one is something that I wrote last year. And these are basically papers that try and do NISQ optimization, so variational quantum optimization on the back end of the designs and back end of the sensors, and try and essentially use feedback loops to get basically beyond short noise scaling. And so this was work by Peter Soller, and where they showed that you could actually, and then and Rainer Blatt and so on, where they showed that you could actually use variational techniques to beat standard quantum sensing. In their case, it was in a regime where they didn't have access to an analytical formula. So what I have shown you till now is if I take quantum sensors where the embedded phase is unknown but constant. But you can also say I take an embedded phase which is essentially drawn from a probability distribution, and you need to find the mean and the variance of the probability distribution, then you can't solve that problem analytically. And so these guys basically said, oh, NISC design is good, and in fact, detectors can be optimized to do this. Okay. And in the case of Monica Schaller-Smith, again, I think out of deep experimental intuition, they just write down what measurement operator to measure, right? Okay. So now let me go to the motivation of my work. So that's kind of the background of what was happening when we kind of took on the question. And the motivation is, I want to throw a dart and choose a state. That's a very good sensor. This is it. That's the entire motivation. And what do I mean by throw a dart and choose a state? Again, I'm talking vaguely in analogies, but I'm very, very happy to talk to you offline about more of the maths of this if you wish. So what I mean is essentially Haar random integration. So let me just introduce that to everyone in this room. So if I take integration over a sphere, basically, I just write the volume integral over a sphere. What you can see is that there is a sine theta d theta in the integral, which means in the evaluation of the volume of the sphere itself, the volume prefers basically to choose theta close to pi over 2. It gives it more value to the integral because sine 90 is 1. Whereas sine 0 being 0, it just shuts the integral off at the equator. So if you now do this for even larger hyperspheres, so if you do it for n balls, then the problem gets even bigger because you have the sine to the power of n minus 2 in the polar representation. And so this is actually an example of what is called measure concentration. So what it basically means is that the volume of hyperspheres are mostly located along the equator. So if you wanted to Monte Carlo sample the volume of a sphere or a hypersphere, and you just put points all over the place and then sample from it, you would actually be getting the wrong answers. And you would actually have to cleverly sample the points on the blocks on the unit sphere based on basically this measure that is sitting here, and that's essentially the entire argument. And so there are two observations here. One is you need to cleverly sample, and the second is that most of the volume is around the equator because this thing basically along all of its sine angles basically suppresses the volume by a factor that goes like phi 1 to the nth power near phi equals 0 and promotes it with the same number, 1 minus that, near the equators. So this basically goes towards the theory of sampling hyperspheres, both complex and real, and the complex ones, that is the unitary spheres we're interested in. And it has a name. This is basically just called Haar integration and Haar measure. So why is this important? Basically, because for the space of unitary operators, typically we have n qubits. The volume is actually 2 to the power of n. So all of this just becomes exponentially worse, right? And very, very quickly, you have very heavy measure concentration. All of the kind of points that generate volume come from a little band around the equator. And any random toss of coin that you do, the random point hits this because that's where the volume is, right? And so if you want to think of it, if you want to imagine it like a cartoon, it's essentially like these SPDF orbitals that we studied in high school. So there's a dumbbell that's going up, but it's essentially very, very skinny along the equator, and it's mostly just a big bulb around the poles, and it's mostly a big bulb around the equator. So when you throw a dart and you want to hit it, you'll mostly hit the equator. Basically, that's the way that I understand it. And so recently, well, maybe 6 7 years ago, it was shown that this thing has a very strong role to play in machine learning algorithms. Machine learning algorithms lock out because of Haar sampling. And so what we did first was we checked as a kind of curiosity the Satin algorithm that Monica Schaller-Smith has. How fine-tuned is it? Where is it on the? Could I have thrown a dart and hit it? And the answer is no. It's actually extremely close to the equator. You can prove this formally. And this is built inside the Monica Schaller-Smith's paper as an argument that the time that it requires for you to apply the squeezing operation goes as 1 over the square root of the number of atoms. So if I take the thermodynamic limit, then the time to squeeze gets shorter and shorter, and electronic noise will cut you off at some point, and you just won't be able to even do the experiment, right? So that's the issue there. Okay. So I just give you an interlude. I present these formulas, but essentially there's a very nice review that I point to you. And these are the first and the second moments of any operator that you calculate with respect to this Haar measure. And the intuition here is just quite simple. And so I present to you the intuition and default the equations to an offline discussion. The intuition here is, suppose I take a sphere, right? So I take some object, and what I do is I keep rotating it and taking pictures of it. And I ask the quantity, I ask you, what can I calculate from kind of collecting all of these pictures that I've rotated, right? It's the rotational invariant object that, with respect to the, it's the rotational invariant property of the object. And for matrices, they're just the trace of the matrix. So that's what you're seeing there. It's basically just saying if you average over unitary rotations, random unitary rotations, the only property that survives an operator O is actually the trace of the operator. And there's some normalization that produces a 1 over D. This normalization is important because this D goes as 2 to the n, right? 2 to the number of qubits. Now, if I have two such copies of the object, and what I can do is I can again perform random rotations, right? Or there are two parts of the same object, but I can perform random rotations, but I have to do the same rotation on both of them. Then I ask the question, what's the property that survives? And the property that survives is, of course, something trace-like, but also the property that is permutationally symmetric. So if there is some property of this body which survives just exchanging the two halves, that survives too. And that's what this formula basically says. So it says, if you now take two copies of the unitary operator over a larger Hilbert space, right? And now you average over this double copy, then there are two things that survive. The first one is basically related to the fact that you have trace-like property. They're actually mixed because of some orthogonality statement. So there is a trace here, and you can see the trace here. And then there is a trace of flip times O. And flip times O is essentially just exchanging the two. And these are the two properties that survive this kind of random rotation pictures and measuring invariant properties, right? That's the cartoon version of what these two formulas are saying, right? So what I want to do is take these two ideas, take these kinds of ideas, and then just essentially design the job of throwing darts and designing quantum sensors out of this. So that's what I want to do. So our protocol, which is just essentially exactly Monica Schaller-Smith's protocol, but we've just essentially taken all of the bits and just blown them up to being anything, is I take some fiducial initial state. It would be well within my choice to choose something extremely simple like 0 tensor n. I should not choose anything complex because then I'm fine-tuning, and I want to avoid fine-tuning. I then do some random transformation that I undo after a while. And then I basically ask the question, I phase embed in the middle. What can I do with these kinds of protocols? Right? And what's the universal theory of them? And so, okay, so you can do this. You can just do the integration, and I've just shown it to you on the wall here. But I'll just make the argument to you by first showing you the formula, and then I'll give you a geometric intuition for it. It turns out that if you just randomly pick unitary operators from a d-dimensional, n-dimensional Hilbert space, so I have an n-dimensional, I have n copies of some d-dimensional Hilbert space, and what I do is I just pick, or n qubits, then I just pick basically a Haar random unitary in SU2 to the n, which means just a complex rotation on all of the n qubits put together. And then I choose that as the initial state. I put it into my sensor, phase embed, untwist, and then measure. I get nothing better than classical Fisher information. That's what this formula is showing you. Right? 1 over square root n is square root Fisher is square root n. So that's that line over here. So what it's saying to you is this thing does no better than classical Fisher information. Now, on the other hand, now I'm showing you two mathematical formula, which I will justify with a visualization in just exactly 1 second. If you choose A to be the symmetric spin operators, such that trace A squared is basically S cubed, and you calculate the Haar average. So if you choose basically symmetric Haar random unitaries, right? Then what happens is permutation invariant Haar random unitaries. Then what happens is that you get a factor that goes as n squared. You lose a little, it's divided by 4 with respect to fine tuning. So fine tuning, the Fisher information goes as n squared. Whereas for us, the Fisher information goes as n square over 4. So you lose a constant factor, but good enough for government work because you just get random sensors which behave extremely well, right? But as of now, as of this equation just now, I've just said a bunch of maths at you. I haven't really told you what the physics of this is. And so what I will do for the rest of the story is basically just tell you the physics of this and also show you other people who've landed at the same example. But before I do that, let me show you actually a geometric intuition for it. So the geometric intuition is the following. So imagine that I have a little square and I'm trying to kind of sense a little angle that it has picked up. If I now rotate over the entire square, what ends up happening is that it generates a blob like this in the shadow. So I'm showing you the shadow that I'm taking on this side. But on the other hand, if I actually rotate in a finite group, let's say I've done this kind of rotation, then I generate these kind of 5 lines. And when you're doing sensors, what you're doing is you're detecting the red versus the green here, a small variation in angle over a random rotation that you're imparting. And the argument is, if you randomly rotate across the full Haar measure, you're scrambling all possible things that are happening. And it can't detect a small rotation that you've done, right? I want to take a picture of an elephant by just taking shadows on the wall. If I just randomly rotate the elephant all over the place, I've left no structure, right, for me to actually see anything about the elephant's kind of design, except to see basically the average projection of the shadow on the wall. On the other hand, if I choose to do 90-degree rotations and take pictures, that's in fact exactly how you would take pictures of objects with 2D cameras, right? And that's the argument here, which is that the many-body quantum physics argument is that you have to preserve quantum correlations in many-body quantum systems to actually be able to use them for things like sensing, but you have to combine them with essentially arguments of randomness so that you also don't fine-tune anything that you're doing, right? So that's the intuition here as to why this logic works. Now, just as a kind of finishing up conversation about sensors for those who are experts on sensors, we can do multi-parameter estimation with this. So this is exactly the full theorem as to how multi-parameter estimation works. So the Fisher matrix you can calculate, and then you can calculate all possible diagonals and off diagonals on Haar random averaging. And then essentially what you get is that you can measure all of the angles that you want and all of the off diagonals fall off. So let me explain the intuition of what the problem is here and what the solution is here, because I'm actually presenting to you quite an interesting solution, if I may say so myself. So suppose I want to measure non-commuting observables. So I have a magnetic field which is pointed in the xy plane. So I want to measure bx sigma x plus by sigma y. And I need to measure bx and by. So I need to measure some property of sigma x and sigma y, but they don't commute, which means you can't know them with infinite precision. They're bound by the Heisenberg uncertainty principle. And so this, as it appears in quantum sensing theory, is the fact that it is impossible for you to simultaneously measure several things which are non-commuting in nature. And the Fisher matrix has this property which basically says that the SLD, the optimal measurement that saturates the quantum Kramer-Rao bound for one of them, will not saturate for the other, and then you have to now kind of switch out. So the argument does not hold if I am constantly rotating the basis, because then what's the big difference between x and y, right? And so you can estimate formally basically all of the different, so you can measure several non-commuting observables. You can directly measure them. Because what you're doing is the entire experiment basically keeps switching between what the x-axis and y-axis is. And so it collects all of these measurements all at once. And you just need to sift through them and you can measure all of these quantities. That's what this thing is saying. And here is the here is the small calculation, essentially showing that this also works for mixed states. So it actually works in the case of some sort of depolarizing maps and so on and so forth, which the quantum state is suffering, and the formal random quantum sensor works exactly. Okay, so let me take maybe, Gunza, is it okay if I go like another 10 minutes, maybe? No more than that, yeah? So let me just very quickly just show you. I don't want to, I have limited time, so I won't spend it on this. So these results we had by basically March of this year. And what we had realized was that we were missing one piece. And this is what I just want to finish up. Before I show you the missing piece, let me show you how other people have approached this question. This question of robust quantum sensor design is something that's been on people's minds. So this is Daniel Brown. And so Daniel Brown basically argued that if you take the kick-top model, so Jz and Jy squared over n, and you evolved it to some arbitrary time, then you actually get quadratic Fisher information. And so this is a piece of evidence that is saying something, and now I have to tell you what the thing is saying, right? And this is a paper by Maciek Levenstein's group, Osmaniak. And what they do is they take basically bosonic modes, which don't have Haar random properly defined, bosonic modes, but they take pairs of bosonic modes and interpret the number operator with a U1 gauge degree of freedom as basically the Haar, the unitary group. And then they do permutation invariants under that, and then they show you a quadratic sensor that comes out of exactly this circuit design. So again, the central argument I just want to make is the following, which is, let me just back up for 1 second. That's permutation invariant. Jz and Jy are collective spin operators. This is permutation invariant in the bosonic modes. So they're symmetric cross-care interactions. So if I have A talking to B, B talks to A, and with the same strengths. And all pairs with the same strengths. So they're permutation invariant. And this is Norman Yao, and he basically says, well, let's consider the following kind of butterfly sensors. So I have a U, and then I embed with it a small V, and then I undo the U, same thing that I just told you. And then I phase embed, and then I do the U again. And what can I do from this? So this is basically acting as a generator of chaos, right? It's essentially like a butterfly term. It generates chaos. It's the same that Monica Schaller-Smith does, but Monica Schaller-Smith directly phase embeds, right? So her little butterfly term is all over the place, but it's phase embedding in nature, right? So the amplifying term. Whereas they do a butterfly before, phase embed, and then undo the thing that they do. And if you look in the appendix of the paper, they basically say Haar average quantum Fisher information over the full group does not yield metrological invariant advantage, only permutation subspaces do, right? So we're all arriving at the same conclusion. We calculated this formally as a quantum information theoretic quantity. They calculated it from various different directions. And the very last example that I want to show you is Petsy and Smirtsy, who basically calculated for random matrix theory ensemble COE, CUE, and CSE. And they basically just say in intermediate times, you actually get very, very good quantum Fisher information from chaotic Hamiltonians. Right? So now what we want to do is basically produce an understanding. First, we wanted to understand for ourselves, and that's the rest of the story, another 3 minutes of your time, with your permission, as to what it is that is happening here, all over here. I want to start all the way from Noon state metrology, the deterministic thing that everyone has been doing for the last 25 years, go through Monica Schaller-Smith, go through Petsy, Smirtsy, and everyone else, and come out on the other side with an understanding that just connects all of these at once, right? And so the underlying, I'll just skip this slide, it's not very important. The underlying unifying theory is the following. And I just present it to you as a kind of 5-point argument or 4-point argument. I don't know why there's a 3 here. Sorry for that. So what does it say? It basically, so I take 1 second to introduce you to random matrix theory. It's the argument that if you have complex nuclei, things where there are hundreds of levels, this was where it was developed formally, that you don't need to look at exactly the structure of the Hamiltonian per se. There are just properties of the Hamiltonian symmetries which guide the level spacing statistics, which is basically, if I take the Hamiltonian and diagonalize it, the EK, this level spacing is just nearest neighbor levels difference. So the level spacing statistics, how many of them have a given gap? This level spacing statistics has a universal property, and it's just derived from the symmetries of the Hamiltonian, whether it is unitary symmetry, orthogonal symmetry, or symplectic. And this tells you something, tells you a lot of universal properties over the Hamiltonian. And if they're integrable, then they tend to have this kind of Poisson distribution, right? And the intuitive argument here is that integrability has huge degeneracies. because what is an integrable Hamiltonian? It just has finite fixed frequencies, which you can integrate and you can exactly write down the answer if that's the way you want to think about it. And then when you wrap it around the Bloch sphere many times to generate the unitary operator, you hit a lot of degeneracies, because it's like taking a rope with periodic beads on it and then just wrapping it around a drum. And because you'll just keep, with large probability, you'll just hit, because it's a finite compact space and you're just taking a real line and trying to fold it on, you'll hit a large number of degeneracies. But when you do it with random matrices, there is level repulsion here, which is you can formally prove. Now, our argument is the following, which is you have this case, which is integrability, and this case, which is non-integrability. When you have integrable Hamiltonians, the orbits are non-ergodic, right? So integrable Hamiltonians are like harmonic oscillators. They just have periodic orbits. They have fixed orbits that are basically trapped inside the integrability region, basically region of integrability, right? And because they have fixed orbits, they don't have ergodicity. They're not all over phase space, all over Hilbert space. Non-ergodic, on the other hand, are exactly all over Hilbert space. And the non-integrable Hamiltonians are ergodic. And because they're ergodic, you can replace the time averages with ensemble averages, and the ensemble averages are all over space. And that property is actually Haar. This is well known from random matrix theory. And so what we did was we basically said, okay, let me take the 0 tensor n, let me take an e to the minus I h tr. H is not G, it's not the phase embedding Hamiltonian. This is the Hamiltonian that I use. So what I do is I assign basically, instead of Haar random unitaries or fixed unitaries, I assign the thing that I'm generating the initial state with, I assign it a Hamiltonian. And I allow basically some TR to be some fixed random time. And that is a kind of randomness that I choose. And the other randomness that I choose is the randomness of H itself, the level spacing statistics of H. So if I choose H to be an integrable model, then it forms orbits. And when I evolve it for some arbitrary time t, I cannot actually simply just take ensemble averages. I have to take the time average. And if you take the time average, you can formally show that you have to fine tune your Hamiltonian. Right? But before that, let me just say, I'll get to that argument. That's the very next slide. Let me just say what the argument with the non-integral Hamiltonian is, because there's one more technical step, which I'm just going to skip, but I'm just going to talk about it, which is if you take, let's say, 2 qubits, right? It's 15 operators, 16 operators, right? SU4. And out of the 16 operators, there are several subgroups. There is SU2 cross SU2, which is a trivial subgroup, a subalgebra. There is a small SU2 cross SU2, so just the operator algebra. There is SU2 cross U1 cross SU2, which is basically 7-dimensional number. There's SO5, which is 10-dimensional number. And then there is SU4, which is 16-dimensional number. So this is an example of actually a finite subalgebra of SU2 to the 3, SU8. These are all the diagonals and anti-diagonals that you can put into kind of some representation. So the argument that exists in control theory is basically, control theory has come up with this notion of dynamical Lie algebras. And so dynamical Lie algebras are basically the following argument, which is, let me say that your Hamiltonian is composed of 2 variables x and y. Then when I ask you to compute formally what the unitary operator attached to it, that's what I'm doing just in the previous slide, e to the minus iht. So when I compute the unitary operator, what I actually do is I take the Baker-Campbell-Hausdorff and I get all kinds of nested commutators. If the nested commutators close in a closed algebra, then I'm done. And I just fold it and I'm done with the unitary operation. If it doesn't, then it forms the full group. So DLAs are basically this nested commutators, is the span of the nested commutators. That's the algebra. And if this dynamical Lie algebra is a formal subalgebra of the full algebra, then the orbits of the unitary operators that you generate are trapped inside a smaller volume than the full Haar volume. So this argument essentially reduces the dimensionality and hence makes symmetries, preserves symmetries. That's the argument I want to make. So the argument is presented here. So the argument is basically that the dimension over which you average right, with the Haar measure depends on the algebra. And this is what we prove in this upcoming paper. It's one of the many results that we prove. So if you actually look at the dynamical Lie algebra of the Hamiltonian generated, and you can take tons of different models, you can have integrable models, which means that the algebra closes and on top of it there are invariants there. Or you could have algebras closing, but there are no invariants. And if you have no invariants, additional invariants, then you don't have closed periodic orbits, and you actually have to Haar average over the space. But that space is a smaller space of the full unitary space. And that is the thing that generates symmetries that I showed you. The rectangle that is the square that is rotated and then slight phase embedding, rotated, then slight phase embedding. The finite rotations are actually the subalgebra, are implied by the subalgebra here. Whereas if you generate no symmetries at all in the full dynamical Lie algebra that the number of qubits allows, this is Haar random integration. And then you scramble away the entire quantum state. There are no many-body correlators left to capture basically the phase embedding that you want to study, and hence you're basically stuck. That's basically the argument that we're providing. Sorry, I should exchange the order of these two slides. I just realized this just now. The integrable argument is essentially the following, which is that if you take, let's say, G is SZ operator, right? This is the phase embedding operator, just collective SZ. I have n atoms and I apply a magnetic field, right? And they're not talking to each other, so this is a collective SZ. If I take an initial state which is like 0 tensor n, sorry, if I take an initial state which is 0 tensor n, and I rotate with it, I rotate it with an x tensor n, right? Then I get this particular state, cos omega t 0 tensor n plus sin omega t 1 tensor n. It's just a one-line algebra to do. And all of these states are quadratic Fisher saturating. But if I start not in 0 tensor n, but I start with, let's say, Hadamard tensor n, so plus tensor n, then I don't get quadratic Fisher information. I get linear Fisher information because I've scrambled the state all over the place. So for integrable Hamiltonians, you need to fine-tune your orbit. You have to sit on an orbit that produces quadratic Fisher information, right? And you could pick just as easily other orbits that don't. This we've known forever, right? If I just said to you, in Ramsey interferometry with SZ, you need to choose noon states to prepare initially, you would not blink at all. And you would say, yes, I've known this result for 30 years now. But the random matrix theory argument that we're presenting, which essentially also includes integrable Hamiltonians on the outer corner as the exception, is basically that when you have integrability, you actually have to fine-tune your quantum states and you can hit Heisenberg sensitivity. Whereas on the other hand, if you don't have integrability, but your dynamical Lie algebra is inside of the full algebra, then you have Haar as the eigenvalues and eigenvectors are doing two separate things. The eigenvectors are actually Haar sampling the entire space, but the algebra is not allowing you to leave this little pocket. And that is exactly what is happening in all of the other things. So GHZ is explained. So let me conclude and make this case. GHZ is explained basically by the fact that that it is actually an integrable orbit of a very nice Hamiltonian, of a nice generating Hamiltonian, and all such examples, cats, and all of them are fine-tuned. So all of the kind of fine-tuned examples are explained that they're integrable Hamiltonians, and then you're using fine-tuning to essentially capture the Fisher information. And we also explain all of the previous results, Petsy and Smertsy, Levenstein, Brown, so on and so forth, by basically pointing out that they've picked, and Norman Yao, they pick permutation invariant operators all the time, right? And Petsy is the closest that actually comes to recognizing ensembles having some relationship to Fisher. But as far as I can tell, there isn't an argument as to why. And the why argument is missing. What is the missing argument? The missing argument is the dynamical Lie algebras. So you need to combine random matrix ideas with dynamical Lie algebra ideas. And in the intersection of these two, you actually realize that permutation invariant Hamiltonians that you could pick just from intuition, from experimental motivation, is an example of this. And with this, you could actually now design entire families of other sensors with things like Aubrey-Andre model and so on and so forth. And that's basically where we're going with this. Yeah, thank you very much. I'm sorry I took a little bit of extra time. Yeah.
We have time for questions also. If anyone in the Zoom wants to ask, just also you mute and ask. Also in the out here. Yeah. Roberto says that thank you for the nice talk. Hope to be able to discuss tomorrow. So any question or comment? So I would like to ask, because the Fisher information is also it's a metric, right? And this has been used a lot in quantum thermo in order to.
Yeah.
But in that case, you want to minimize it, right? So the geodesic, so the Fisher information is a metric, and then you want to find the
Bure's metric is something like 1 minus Fisher. Bure's distance between two neighboring states is something like 1 minus Fisher squared divided by 8.
Okay.
So minimizing the metric is the same as maximizing the Fisher.
Okay.
Yeah.
So then this can be related to kind of finding the geodesics of your metric. So in the sense, so you may so for a given problem you may want to maximize Fisher information, right?
Yes.
And for that you may find the geodesics of the metric.
Yeah, I mean, this is how it's formally even defined. I mean, so Fisher is defined, if you look at any of the reviews which carefully calculate it, Fisher is defined with respect to kind of more formal distance measures like Bure's.
Okay.
And there it is just, if you calculate the neighboring, it just goes as 1 minus, Bure's distance goes as 1 minus Fisher square by 8 is what I remember, but maybe I'm off by a factor.
So can you, for example, relate this with, for example, with the Beer's distance as well, right? I guess
we haven't done it because so Fisher is such a fundamental quantity for sensors that you don't need to make any additional comments where it comes from. But if there is an argument you want to make about Beer's, then we can talk. It directly follows. I mean, so the central argument here, Lalo, is that Fisher information for pure states, that the fact that you can write it as 4 times the variance, simplifies your life very easily because the Haar average over pure states is very trivial. But mixed states is also completely straightforward to do. So if you have like some quantity that you're trying to ask, what is the average, randomized average quantity that I could calculate, then let's chat. It's been done for all kinds of crazy things now. Inside of randomized benchmarking theory and measurement-induced phase transitions and all kinds of other fields. So, I mean, we realized basically that we had missed the bus a little bit. That there were all these nice calculations that were there for almost 10 years, and so I learned it in the last 2 years just to do this.
Yeah. Thank you. Yeah. Is there any other question or comment? Otherwise, we can just thank.
Okay.
Okay. So Sai is going to be here today and tomorrow.
Yeah.
And if you want to have some chat with him, he will be around.
I would be very grateful. Yes. Thank you very much.
So let's thank Sai again.
So is Roberta still online? Oh, okay. Yeah. Please thank her, which is